Okay, so I'm going to talk about induced electroweak symmetry breaking. I'll, of course, explain exactly what that is. There's some previous works on this from 2011. I'm going to be mainly talking about something that will appear. Hopefully, it'll be on the archive. Hopefully, we'll post, say, tomorrow. So, I mean, we're really finishing up. So, unless somebody finds a serious problem here, I think we're just going to go ahead and post. So, the Higgs has been discovered. The Higgs, or something almost like it, has been discovered with a mass of 126 GeV. And so I'm interested in the possibility that physics could still be natural. In fact, that physics could still be supersymmetric. And there are various problems with that. And one of them is, and I'm only going to talk about one of them, which is the value of the Higgs mass itself. So the fact that the Higgs is light is has this mass is sort of a blessing and a curse at the same time for supersymmetry. Supersymmetry wants a light Higgs, but it really wants a Higgs that's even lighter than this, right? And so this problem manifests itself in various ways in different theories. So, for example, this is things that we all, I think, know. In the MSSM, the problem is that the tree-level quartic in the MSSM gives us a Higgs mass that is below mz. Okay, so there are various ways of fixing this. Within the MSSM itself, we can get a contribution to the Higgs quartic that grows like m stop, log m stop. But the problem with that is that it also gives us a contribution to the quadratic term that grows as m stop squared. This is something we don't want because it's something we have to tune away. It grows quadratically. This only grows logarithmically. So this is actually already quite fine-tuned. Well, it's already getting tuned. It makes us nervous. So I'm taking that seriously as a motivation. Then there's another approach is the NMSSM. And I'm including in this what's called lambda SUSY. So just to add another scalar, you have another source of a quartic. Another possibility is non-decoupling D terms and or a fat Higgs. These are closely related ideas. And in all of these right here, the idea is always to get an additional contribution to the Higgs quartic, because we know in a simple Higgs potential that the mass of the Higgs is the Higgs quartic times the Vev squared. So we've experimentally measured this, so we need to increase the Higgs quartic. Okay? And I think there's definitely motivation with these sets of ideas. What we're doing is actually probably most closely connected with this, but there's definitely some motivation for trying to go beyond these things that have been studied quite a bit. One of them is that these ideas, at least except for this one here, have some tension with unification, okay? Because the additional structure that here you have some Lian-Tao pole issues. Here you need a lot of additional structure to get unification. And also, in a lot of these cases here, if you care about naturalness at all, you only get naturalness for a very, very special restricted set of parameters. So I would say that's something that's true both in the MSSM and the NMSSM. If you want to have the theory be as natural as possible, you're restricted to a very narrow range of parameters. Okay, and so this situation has led a lot of people to consider the possibility that maybe the theory is tuned, and if it's tuned, it's allowed to actually be a lot simpler. So there's a tension between naturalness and simplicity, and some people are saying, well, maybe SUSY opts for simplicity, and that's certainly possible. But what I'm going to do is I'm going to take the sort of old-fashioned point of view that nature does like naturalness. It may be just a little bit more hidden than we thought. And I feel that that's part of our job, because part of our job as particle theorists is to test the idea of naturalness. Okay, so that's the way I'm looking at this. So there's a new idea, I would claim, in what we're doing, which is that the new idea is that we're going to have some additional Higgses, some auxiliary Higgses. So we'll call those generically sigma. And we'll call those auxiliary Higgs fields. Okay. And the thing that makes them different is that they have no Yukawa couplings. They have Vevs, but they have no Yukawa couplings. And the point of that is that if you don't have Yukawa couplings, it's easier to get a big mass to have a big quartic for these guys. Okay, it's easier to get a big quartic, as we'll see. So just to give you an idea, just to make clear what I'm doing, so V, this is the thing that's 246 GeV. This is now a combination of the up and down quark vevs of the MSSM, but then there's a new contribution, F, that's coming from these auxiliary Higgses. And just to give you an idea, the kinds of numbers, typical numbers that I'll be talking about, F will be, say, around 150 GeV. Okay? And so that means that the rest of these guys, V up squared plus V down squared, is about 195 GeV, right? I want to just emphasize the elementary point that it's the sum of the squares that matters here. So even a fairly beefy Vev F here still allows a very large Vev here, okay? And remember, these are the ordinary up and down type Higgses are the ones with Yukawa couplings. And so you can see that you can still easily get a top quark Yukawa, a top quark mass from a theory like this. Okay, without any very large Yukawa coupling. Okay, and these, of course, I've added new Higgses, so there's going to be new Higgs fields, there's going to be new Higgs particles, and all the new Higgs particles are going to be above 125 GeV. So the Higgs that we've seen is the lightest Higgs. It's going to be dominantly made out of the H up and H down. These other Higgses are going to be heavier. Okay. Now, there are two kinds of, so therefore I can talk about the theory, the effective theory below these sigmas right here. Okay, so I'm going to tell you what that is to give you an idea of what the mechanism, what is the new mechanism here. And there are actually two limits that are interesting here.
Marcus, I have a question. So
yeah.
Is this actual field to be heavier than 125, is that a requirement or it's guaranteed?
This is what we're imposing, and as you'll see later on, this is what I'm describing to you now. I'm making this assumption here so that I can tell you what the effective theory is below the mass of these auxiliary Higgses, and that will basically be a way of me telling you what the mechanism is. In the end of the day, this is going to be some multi-Higgs model with some parameter space, and the two things that I'm going to describe now are just two different limits of that parameter space that are easy to understand. But this is the way I want to tell you what the basic, this is the way I want to try to describe what the basic mechanisms are that are at work.
Marcus,
yeah.
Also, those sigmas are heavier than A, what is normally called A, and capital H in the MSSM?
I'm leaving that open right now, okay? But if you want to, right now I'm trying to describe some limits of this where the mechanism is easiest to understand, and the mechanism is easiest to understand if you just assume that all of these guys are heavier than all of the MSSM Higgses. But at the end of the day, I don't really need that, okay? All right? So let me.
Sigma coupled to the use of Higgs vector?
Yes. So actually, let me maybe draw a diagram. So what I'm assuming is we have some sort of SUSY breaking sector that feeds into the MSSM. Okay, but then I have this sort of auxiliary Higgs sector, okay, that has these fields sigma in it, okay, and some other fields that I'll call phi, and we have some interactions between, and SUSY breaking happens at a TeV in both of these sectors, and we have some couplings that that are sort of look like this, okay. There's sort of some trilinear couplings between Higgses here and Higgses here, and these guys are going to influence the Higgs potential of this guy right here.
But you're not going to allow any coupling between sigma and the top, let's say?
Right. It's not that I'm not going to require it. My theory won't even allow it, as you'll see. Okay. Okay. So let me give you one example of this kind of setup, and this is the example that we studied in these papers right here. Okay. And the reason that you don't work on this is because it's called SuperConformal Technicolor. Okay. Even though perfectly okay with 125 GeV Higgs. So here, the idea is that what this sector is right here, what this sector is it's actually a strong conformal sector. It's strongly interacting and conformal. And at the TeV scale, SUSY feeds in TeV masses to both of these things. This thing confines. Okay, it breaks SUSY, that triggers confinement. This breaks electroweak symmetry. So in this extreme version of this model, you can think of it as an extreme version of this model, these sigmas are really some composites from some Technicolor sector. Okay? Technicolor is famous for being a good way to break electroweak symmetry, but a lousy way to give you quark and lepton masses, right? And so here, I don't require these sigmas to have any Yukawa couplings at all. Okay? So I just have a very strongly coupled electroweak breaking sector, and then interactions between that and the MSSM, interactions with the Higgs with operators over here, basically give us new contributions to the Higgs potential that make this natural. Okay, that make the Higgs mass completely natural. So I'm not going to describe these in detail because I'm going to go into great detail about the perturbative model here. Okay, let me just tell you, because I'm actually an honest person, I'm going to tell you why the worst thing about this theory, and that is the S and T parameters in this model. Okay, this theory here, even though the VEV, this is some Technicolor theory with a reduced VEV. So in the first microsecond that you hear that, you might say, oh, well, that's a great idea for precision electroweak because your S parameter will be reduced. Because surely the S parameter goes to 0 when F goes to 0, right? But that's incorrect. In the next microsecond, you will surely realize that that is incorrect because I'm taking this funny limit where the mass of these states is much heavier than the 125 GeV scale. If it's 150 GeV here, the heavy resonances of this Technicolor sector are at the TeV scale. And below that TeV scale, electroweak symmetry is nonlinearly realized, just like in Technicolor. And the S parameter is a dimensionless thing. Okay, so it does not go to 0 with F. It's like the S parameter is something like F squared on top and M rho squared down below. But this is like F squared over G rho squared F squared, right? So the F squared goes away, and it's an unsuppressed Technicolor size S. And now you're convinced that it's ruled out, which is too bad because it's not right. Because if you actually look at a minimal Technicolor theory, like we have here, the contribution to the S parameter is around the same size as the ellipse with large uncertainties. And a positive T parameter that you naturally get in this model can easily put you back into the 95% confidence level ellipse. But never mind, because you don't believe me. No matter what I say, as soon as you see Technicolor, you think it's ruled out by precision electroweak, and I'm not going to argue with you, okay? But that's what we did in those. I'm just describing to you what we did in those papers.
Markus Luty or Ken Lane just came to this room and is.
I don't think. Do I look like? Do I sound like Ken Lane? Do I look like Ken Lane? I don't know. Anyway, so I would claim that this type of model is actually totally okay. All right, it's sort of marginal with respect to precision electroweak, but no worse than that. But you don't believe me, so we won't talk about that.
If I were to believe you, what would you say is what we have discovered at the LHC?
Oh, you've discovered the light Higgses. You've discovered a mass eigenstate, which is mainly made of the MSSM. You discovered what you thought you discovered. You just didn't know that there was also this Technicolor sector at a TeV. Sitting on top of that, giving you important contributions to the potential of the guy that you discovered. That's all.
So, Marcus,
okay.
The 125 Higgs is mostly up in
Yeah.
But then that Higgs will have a reduced coupling to the WC boson.
Right. But not very much. I mean, we definitely will. I will show you plots. I will hand draw them. But we put that constraint in very, very definitely. The point is the uncertainties on that are large enough that you still allow a substantial mixing with this sector.
It's a substantial deviation, though, because for these numbers you gave here, the couplings are about half.
What coupling is half as big as what other coupling? I don't understand.
The coupling of the Higgs in your theory compared to the standard.
Oh no, it can be as close as you want. You'll see. Just hold on a second, okay? It can be. No, I mean in this theory also you can only use NDA to estimate things, okay? But if you do that, you can very easily be consistent with the Higgs couplings. So, but see that you don't believe me. So let's forget about this model, okay? You don't believe me. I'm going to do the whole point of this talk is that I want to.
For the reason you're saying.
I'm sorry. Boy, I can't please anybody, even if I'm right.
Already. He wants to know the couplings of the Higgs to W.
Yeah, but let me. I think it's in this model. This was all just to introduce this. So,
it seems that we are also interested in the 1106 paper.
Well, I think you'll be even more interested in it after I tell you about this paper, okay? Because what I want to do here is give you a completely calculable version of this same mechanism. This is a perturbative model. There's a Lagrangian. You can calculate everything. You can calculate precision electroweak. You can calculate the Higgs coupling. You can calculate everything. You don't have to take my word for it. You can check it yourself, and everything is fine. And one limit of that theory is a theory like this. Okay, so then I think that will be a great way. Also, if you want to understand this, I think this will be a good way to explain that. Okay, so the theory that I have can all the important physics of this theory can actually be described by what we call a super simplified model, because it's even simpler than the simplified model that's in our paper, so we had to call it something. So here's the complete Higgs potential of this theory. Okay. It has masses, it has two Higgses. It has has a normal Higgs doublet and one of these, the auxiliary Higgs guy. Then it has some mixing mass between them. Okay. And then only the auxiliary Higgs has a quartic. Okay, so this is the theory. Okay.
So this is the standard model now. Just one Higgs.
This is my super simplified model. I'm not writing every term that's allowed by symmetries, if you notice, right? I'm simplifying the model to bring out the essential physical mechanism. So the idea is that this is the guy that has Yukawa couplings. He's going to have also most of the VEV, right? This guy has no Yukawa couplings, but he has a big quartic. And I'm neglecting every other quartic that you can write down. Okay, and so in this theory, I have VEVs for, I'm going to have VEVs for both sigma and for H. So electroweak symmetry breaking is shared between these guys, right? And I'm going to assume that the light mass eigenstate, H1 light CP even guy, is the 125 GeV Higgs. Okay, so now if I fix the fact, let me call this V sub H. So I know the total VEV, 246 GeV. I know this mass. So this theory has two parameters left, right? And those two parameters I can take to be F, the VEV of this auxiliary Higgs, and lambda. Okay. So if you just solve this theory, it's a standard 2 Higgs doublet model, and you just ask what does the parameter space look like in this plane, right? Then you know that F can only go up to 246 GeV, obviously, right? F cannot be bigger than that, okay? And then what you find is that for every value of F, there's a minimum value of lambda for which this model works. So if you're down here, what happens actually is that what you get is the theory becomes unstable, okay? If you cross this line, you don't have a stable minimum. Okay, and actually a little bit below that, what happens is that the H2, you get stable again, but the H2 becomes the 125 GeV state. I don't want to go there. Okay, so we just have a lower limit like this.
What is H2, Markus?
What do you mean? What is H2? Is the second CP even mass eigenstate. There are two CP. This is a 2 Higgs doublet model, so there are two CP even Higgs doublets, right?
H1 is even
Higgs. Huh?
H1 is lighter than 200.
Right. Right. There's an even lighter Higgs, and I just don't want to go there. I think that's crazy. Okay?
So here
Somebody else can write that paper.
So here you assume there's no radiative correction in that, right?
Yeah, this is a totally super simple. I'm just bringing out some really, really simple points.
Is sigma doublet? Yes.
Yes.
Sigma is a doublet.
Yes.
Okay.
There's nothing up my sleeve, I promise. This is just some stupid 2 Higgs doublet model. I'm just looking at a particular subset of the parameter space of 2 Higgs doublet models. That's all I'm doing. Okay? So now, what is happening as we approach this line? Okay? What is happening for a given value of f, let's say, we make lambda as small as possible. What's happening here is that we're taking the decoupling limit. Okay? What's happening here is something that's very familiar. You've got one Higgs that has got no VEV, okay, that's getting heavy. And so the way this works is that, let me define a mixing angle, gamma, okay, to be the thing, it's like the analog of tan beta. But I don't want to use tan beta because I'm eventually going to have SUSY where I have an H up and H down. So I'm going to call it gamma. And it's just tan gamma is just the ratio of these Vebses, right? And so what I'm doing is, remember that in this parameter space, I'm holding, I want to take, as I'm approaching this limit going down like this, I'm holding V and F fixed. So I'm holding this angle gamma fixed, right? So what I've got is I've got there's a heavy Higgs doublet, H2, which is just cosine gamma minus sine gamma sigma. Okay? In other words, there's a Higgs, this is both the mass eigenstate and the Veb eigenstate, namely it has 0 Veb. That's the decoupling limit. But it's a linear combination of H and sigma, right? That's all, just because I've taken a general quadratic term here, right? And so the low energy theory, I just integrate that guy out. And what is the effective potential? Well, there's an H1, which is the orthogonal combination, and I have some mass for that, which I could work out by diagonalizing that thing. And I have a quartic, which is proportional to cosine gamma to the 4th for this H1. Okay? So what's happening in this limit right here, as you approach this line from above, is very simple. There's one linear combination of sigma and H, which has got 0 Vev, which is getting heavy, and you integrate it out, but you induce a quartic. There was no quartic before for H, the guy that has Yukawa couplings. Of course, the Yukawa couplings are also suppressed by cosine gamma, but you see that you're inducing a quartic. All right? So that's one limit of this very simple model. Okay? All right. So now you can ask, okay, what happens? So that's what happens near this line. And obviously, one of the things that's clear about this line is that we approach the standard model there, right? You might not like this decoupling limit, but at least you know that all of the couplings of this H1 are approaching the couplings of a standard model Higgs in this limit. Okay? And then we're allowed, we can ask the question of how far are we allowed to deviate from that based on experiment, right? Okay, but now let me go in the opposite direction. So that's what happens when I went here. What happens if I go up this way? So I fix F, and I start just increasing lambda. Okay, and I just ask what happens there. So it turns out that we can just do a little calculation. You can see what happens. What happens is that so now we'll take lambda up, okay, and we'll fix F. What happens in this theory? What happens is that, first of all, m sigma squared goes to 0, okay? And then it goes eventually to negative infinity. So if I really, really go, of course I'm not going to go to lambda equals infinity, but if I just keep going to lambda infinity, what happens is that m sigma squared changes sign. Okay, so there's some place here where some line like this, where m sigma changes sign. And in this theory, in this limit right here, the physics is completely different. In this limit right here, what happens is I've got a big negative m sigma, okay? And in this case, what I can do is I can treat kappa as a perturbation in this limit, okay? Because there's one entry, at least one entry in my mass matrix, which is getting huge, okay? Whereas this one is staying fixed, as it turns out, okay? And so what happens here is that you treat kappa as a perturbation. Now again, my Higgs potential looks very simple, right? If I'm treating kappa as a perturbation, then this is just, in the limit where kappa is 0, this is just two decoupled Higgs potentials, right? And so what happens is the auxiliary Higgs guy just breaks electroweak symmetry all by himself, right? So what I have is I get a Vev for sigma of order F, and on the other hand, the mass of the heavy states here is of order lambda times F squared, right? And that's going to infinity in this limit, so the Higgses are getting very, very heavy.
So you held the total electroweak symmetry breaking of 246. That's
what I am holding fixed. And so in this theory right here, as I've described it so far, the effective theory below this mass, right, has got electroweak symmetry broken, or nonlinearly realized, has an explicit, or if you like, nonlinearly realized W mass, which is, g squared over 4 F squared. It's too small, but it also has this Higgs in it, right? This light Higgs, which hasn't spoken yet. And we turn on this kappa, and we treat it perturbatively, and you can just see that the first thing that happens, the leading thing that happens at first order in kappa, is that I replace the sigma by its Vev, and it gives the Higgs a tadpole, Okay? So there's a tadpole for the light Higgs. And so the important terms in the effective Higgs potential are equal to mh squared, right, plus, times, let's say, little h squared. So I define a CP even. Let's look at the CP even Higgs potential. Minus kappa squared f times h. Okay? Plus blah, blah, blah. Okay? And so now, and this is allowed to be there because electroweak symmetry is nonlinearly realized. And now you can see that what you want is you want mh squared to be positive, okay? And this gives you a VEV, which is just, you get by solving this thing. It's kappa squared f over mh squared. So the tadpole generates, I should call this perhaps VH, right? Because it's now the sum of the squares of this and f that add up to the usual thing, right? So you generate the bulk, since VH is bigger than F, you generate the bulk of electroweak symmetry breaking by this tadpole mechanism. And this is the limit, which is the SuperConformal Technicolor-like limit, because this is the limit of very large lambda, as you see. Okay, so SuperConformal Technicolor you can think of as this sort of limit where lambda is even 4 pi, or I guess it's 16 pi squared, actually. Okay. All right. So these are just, and you can confirm all of this. Look, this is not rocket science. You can all diagonalize 2 by 2 matrices and check all of these statements for yourselves. This is really true. This is really how this model works. Okay. And of course, when we have plots, we actually minimize potentials. We don't write down these theories. Okay. But even yes.
Sorry, Marcus. Why can't I write a sigma dagger h mod squared?
Oh, I can write all kinds of other things. And in the end, we do write everything that's actually there. But my claim is that these are the important couplings. And when we do scans where we scan over all parameters except these two, they look exactly like they do in the super simplified model. So all I'm doing here is just showing you the minimal stripped down model that contains the mechanisms. That's all I'm doing. Okay? All right? So it's not. This is not supposed, and it's not. There's nothing that's zero here that it's essential that it's exactly zero or anything like that. Okay, yeah. So let me just. So I can even in the super simplified model. Okay, I can already tell you what the constraints are. Okay, because so let me actually. I've got a couple of plots where I'm going to write them down with numbers. So I'm just going to sketch these because it's not worth giving a whole. So these are actual numbers now from our plots, and this is about 0.5. They're not exact numbers, but you'll see our plots in our numbers here, and here's around 2.25. And so this, first of all, this region that's ruled out by vacuum stability looks like this. Then there is the region that's ruled out by Higgs couplings. Looks something like this. So this is ruled out just by the fact that this Higgs looks standard model-like. You can see if you deviate too much from this limit, you screw that up, and that hits 3 at about 170 GeV. And then in the middle, there's this line here. This is just the line where m sigma squared equals 0. So you can think of that as being, far away from this line is where you get into the decoupling limit, where you induce a quartic. And this limit, if you go far this way, you're inducing a tadpole. Okay, and this is about 140. Okay, so this is roughly what these plots. This is what these plots look like.
What is the relevance of the number 3 in lambda?
That's where I would start to say that maybe perturbation theory is breaking down, but maybe you would have another number. You can maybe you would be willing to go higher. But I'm trying to make a perturbative calculable model, so that's what limits how big this can be. But what the message is that there's a large region of allowed parameter space which is perfectly perturbative. Okay. All right. Okay, so now the rest of this talk is just going to be to tell you that we can make sensible models in SUSY that look just like this, okay? Where these are the important couplings. Yes, we write down everything that there is, but these mechanisms that have a parameter space that looks just like this, that's the rest of the talk. So maybe now I should just sort of pause and see if the basic mechanism is clear.
What's the superpotential?
Well, okay, you want to know what the SUSY model is? I'll tell you what the SUSY model is in a second. This is just the potential. So yeah, I've got to show you now that I can really do this in SUSY, that I'm not just making up.
Oh, I see.
That's the rest of the talk. So But this is the basic mechanism. I'm aiming to get a potential. These are the important terms in the potential. I need this to be large, as you can see from here. I need a pretty big quartic, right? Okay. And by the way, let me mention one other thing, since this is very general here. This is kind of arbitrary, using this line right here to be the boundary between these two limits, right? You can think of this as an induced tadpole limit. This is an induced quartic limit, right? What you get by integrating. And in between, you've just got a mixed scenario where the auxiliary Higgses just mix with everybody. But one thing you can ask is, instead of using this, I can say, well, when is the quartic, the quartic of the light Higgs, the quartic that I'll eventually measure by measuring the cubic coupling of the Higgs, right, of the 125 GeV mass eigenstate, when is that equal to 1/2 of the standard model coupling? And that's essentially exactly the same line as m sigma equals 0. So, because remember, in this part of the, sorry, I should actually only talk about this after. This only makes sense to talk about after I've talked about SUSY, because here I'm assuming that I just have the tree level SUSY potential. Okay, and the point is that in this part of the space right here, the electroweak symmetry breaking is dominated by this induced tadpole, and the quartic coupling of the light Higgs mass eigenstate plays no role whatsoever, and so it can easily be much less than the standard model value. Okay. So this region is sort of particularly interesting, I think, because of that. All right.
The region that you said is ruled out by Higgs properties, what property specifically is setting that line?
Mainly just the couplings to gauge bosons. Just what Scott was saying is that if you do too much of this, too much of a good thing, right? If you just keep pumping this thing up, you've got a very big F. And you can see that if F, yeah. So if you're just going to, you can't possibly maintain the couplings to W's and Z's correctly. But okay, so.
So Marx,
yeah.
For the phenomenology part, so this is just pure like a two-stop model.
Yeah.
And the property of the heavy Higgs or light Higgs were just independent of supersymmetry, correct?
Yeah, that's right. I mean, you could study this very much just in the context of two Higgs doublet models, and I would actually recommend that for phenomenological studies.
And my guess is that probably people explore the two Higgs doublet model, they have already covered this parameter space.
Well, my message is not supposed to be that this is going to be hard to discover. These Higgses and all of this region here, just like any two Higgs doublet model, the constraints on the Higgs couplings are already telling you that either you can have very, very decoupled Higgses, we can always have those, right, or if they actually contribute to electroweak symmetry breaking, you can search for them, and they're just from standard Higgs searches. So I agree that the phenomenology of this is just the phenomenology of a two Higgs doublet model. I think that perhaps it's not so. This gives you, I think, a motivation for a region where you can have a small quartic, which I think is interesting. I don't know, but there's so many papers on the two Higgs doublet model. I'd be surprised if this wasn't lurking in there somewhere. I'd be happy to, I don't know where though. I don't know where this kind of limit has been talked about.
Well, it's like a Fermi photon, actually. It's called type 1.
Well, this is irrelevant. I haven't said anything about Yukawa couplings here, except that I've said that this guy has no Yukawa couplings, but that actually doesn't matter for any of this.
I know, but that's Fermi photon. The extra guy doesn't couple with Fermi.
Yeah, okay, sure. But I'm saying that this induced tadpole mechanism and resulting in this small quartic, I don't know if that's where that's been specifically discussed.
So just looking at your potential.
Yeah.
So the large quartic for sigma looks like that's the one that breaks, gives you a large T parameter, right? Because you're breaking the custodial symmetry between these two doublets.
So we do include the custodial breaking between these doublets. That is not the biggest source of electroweak corrections, as you'll see, but we definitely include that in our when we constrain our theory. Okay.
But I'm a little bit worried about additional terms that you could add to the potential. Can you envisage some additional symmetry that restricts it just to that? No,
but these are the important terms. So I'm just displaying the simplest model, super simplified model that has the mechanism. In the end, I'm going to show you a supersymmetric theory, which we write down everything that's allowed, and with this same structure emerges. Not exactly this potential, but the same basic structure emerges. Okay.
So if you have bond that big? Do you have a problem with the projectivity and things like that?
We're going to talk about that. So the answer is yes and no. Okay, so you'll see. Okay, but I'm definitely going to explain the situation. Yeah, because you do notice those couplings are somewhat large, right? And that is an issue. So we'll talk about that. Okay.
Can you
Yeah.
say again, I forgot, what's your attitude on the S parameter? It's super.
We're going to include, this is a calculable model, we are going to include all contributions to the S and T parameter, and we're going to require that this thing has a good precision electroweak fit. That's my attitude about precision electroweak. No, this is a perturbative model, calculating it, right? This is.
I meant in the strongly.
Oh yeah, in the strongly coupled thing, we do an honest, what we claim is an honest job of NDA, and we say that this is the constraint, and it looks like it's on the edge.
So the answer is there's some other contributions that are moving it back.
Well, there's naturally in that model, because there's an H up and an H down that both couple to the strong sector. There's a natural source of custodial electroweak breaking. There's also a natural size for this, which gives you the right size of the tadpole, and that gives you a natural size for the T parameter. And that T parameter is positive, and it has naturally the right size to get you back into the ellipse.
I see, sorry, so S is still big, but
Yeah.
T is such that.
Yeah. Okay, and of course everything has big uncertainties, but we claim we've done an honest job of doing that, and it looks like it's on the edge. That's the status. That's what I would say is the status of precision electroweak. So I don't think that model is ruled out.
Okay, so both S and T are big, but inside.
Big meaning as big as big meaning as big as not these things where it's like 50 times, right? Yeah. Okay. So the models. Let me tell you. Let's construct some actual models. And so the thing I have to tell you, if I'm going to make a supersymmetric model, is where does this big quartic come from? And this big quartic is going to come from new D terms. So I'm going to have a model where I have some new Higgses, some doublets, sigma down and sigma up. So these are up and down. These have the sigma down and sigma up have the same quantum numbers as the up and down type Higgs doublets of the MSSM. But now there's additionally some new gauge interaction, which is where the indices are contracted here like this. So these new Higgses, in addition to electroweak indices, they have some new SUN gauge index. Okay, and that new SUN gauge interaction is what's going to give me the quartic, the quartic. Okay, and so these Higgs's phi's, these are singlets. These phi's are singlets under electroweak. Okay, but they're charged under this new group, and they also have a VEV of order U. Okay, and remember my sigmas have VEVs of order F. Okay, and so this U breaks the new gauge group, which I'll call GS. Okay, so this breaks the new gauge group, this U VEV, and notice this U VEV does not break electroweak. Okay, so this is a VEV that breaks this new gauge group, but not electroweak. So just to give an idea of what the scales are going to be, I'm going to tell you about what the effective, the scales in the effective theory look like for the case where we have the induced tadpole. It's a little different in the other case, so I'll do this case. So the first scale that you hit is this scale GSU, okay? And that's the scale of, let's call it W prime. That's the scale of the new gauge bosons associated with the group. And S stands for strong or semi-strong or something, because I need a fairly large coupling here. So this guy is, and this is going to be something, okay? And so above this scale, I have G strong cross SU2 weak cross U1 hypercharge, okay? And then below this scale, I break SU2 strong, but I haven't broken yet electroweak.
Is it important that the GS is completely broken?
It may not be, but in our model it is. It certainly makes it easier to think about the phenomenology. In the end of the day, in our model, GS will just be SU2. Okay, you're welcome to look at other non-minimal cases, but we haven't. Then the next scale that you hit is GSF, okay? And at that scale, you break electroweak down to U1, because this F is the VEV of this auxiliary Higgs right here. And then finally, this is U1 electromagnetism, finally you hit the scale MH, okay?
So that GS group is that necessary? Can you just have a superpotential to generate a sigma?
That's the other model that I'll talk about. Okay, I'll talk about that very briefly at the end. In the end of the day, we think that for various reasons this model works better, okay, than that model. But that's the other. We looked at that possibility also. Okay, yeah.
You were advertising your unification credentials, so these will eventually. Sigmas will eventually be complete SU5?
Yeah, so that's actually the very next thing I wanted to say is that, yes, these multiplets right here, all the things that are charged under GS, I'll just complete them into SU5 multiplets if I want to have unification. And it turns out that, well, yeah.
Did you say there are D terms besides?
What I mean by D terms, there are 10 things called D terms in supersymmetry, right? So when I say D terms in this talk, what I mean is just the quartic terms in the potential that are induced by having a gauge group, right? The thing that is, right, the thing that is G squared over, 8 or something, sum over the generator is dA squared, right? This is what I mean by the D term in the potential. I don't mean, for example, phi A Heliopolis terms or, okay? Which tadpole? Well, so they comes, you can see it here, okay? This guy gets a vev U, this guy gets a vev F. Below that scale, for example, from A terms or from, if I have mu terms here, I'll get mixed terms that give me a tadpole for H up.
So you need a mu term for that.
Yeah, I mean, that's right. I would need standard mu terms, or I could use A terms if I really. But I need the mu term anyway for Higgsino's, right? So I can't, right? All right.
You're not telling me anything about SUSY breaking.
No, I mean, I'm going to factorize these problems. I'm going to assume that somehow SUSY is broken in a way to give me a not totally unnatural spectrum. And I'm just going to treat the SUSY breaking parameters as free parameters.
That's the same attitude about the mu problem.
Yeah, I don't care. It factorizes, right? So, okay, so Ronnie was asking about unification. These guys are going to come in complete SU5 multiplets. So for now, that's enough. I've got to worry about Landau poles and all that, but we'll get to that. Okay?
So unification is just 3-to-1 unification. GS won't unify with these guys.
Yeah, it might actually, but I'm not going to. You'll see. I don't. But I'm not requiring that. Okay. Okay, but one thing you can already see at this level right here is that if you think about it carefully, you'll see that this sigma right here violates custodial symmetry, okay? Because the fact that I have both vevs for phi and sigma means that the gauge bosons of this GS and the electroweak gauge bosons are mixing, right? And so there will be a tree level contribution to the T parameter. Okay, and so when you just require that thing not be too large, that's going to already tell you that U is going to have to be bigger than about 2 TeV. Okay, because of course, really to make this statement, I have to put in everything. We will, but this is roughly the statement that you get. Okay, so a lot of what I'm saying here, Antonio is nodding. I don't know, is Tim here? I don't see Tim. Maybe he had to leave. But anyway, a lot of what I'm saying right now is kind of copied from the playbook of the non-decoupling D-term models that various people have worked on. There too, I'm trying to get a quartic to be large from D terms, and I have a similar problem. I have some new gauge group. I have to break it, and I have to make it sufficiently heavy. Yet another thing that I'm copying from their playbook is the fact that this is dangerous because these same D terms here that give rise to this potential can now give me a tree level contribution to the masses of these sigmas and H's, which is the things that I'm trying to keep light. And that's a tree level problem, not even a loop level problem, right? However, that can be avoided by having the D terms associated with these phi vevs. Okay, these D terms have to be basically much smaller than phi squared. So you basically have to break this SU2S or this GS along an approximately D flat direction. Okay, but you can do that. It's okay, and then you don't have any problem. But I just want to any tree level problem about tuning. But I want to emphasize that that's something we take from the playbook of these models. The big difference between our model and the non-decoupling D-term models is that in those models, people tried to embed our Higgs into this. So they had a bunch of issues that we do not have to worry about. One is unification. Why should this gauge group, which is bigger than SU2 cross U1, why should this theory unify the way that the minimal SU2 cross U1 theory does? That's one issue. Another issue is how do you write Yukawa couplings for this guy, in particular the top quark? Okay, we don't have any of those issues. This is much more modular in a sense because we're trying to explain this quartic, and this sigma doesn't have to have any Yukawa couplings. You can just be part of a complete SU5 multiplet. So these issues are, I would say, simpler in our models than they are in those models.
Also, in those models, we were trying to write the Higgs mass much more than what it is nowadays.
That's right, that's right. So here, actually, we have the same, if you like, embarrassment of riches. This model would be very happy with a Higgs mass of 300 GeV as well. So it's too bad nature didn't take advantage of that opportunity, in my opinion. But I don't get to choose, so.
Nature is like that, Markus.
Yeah, apparently. Okay, so I'm just trying to give you the main features of this. So I claim that we can reduce the tree level tuning, but we still have a problem. We still have a potential problem at loop level because these states now, remember the masses of these heavy gauge bosons are of order GS times U. So you have a small hierarchy. You require a small hierarchy among your SUSY breaking masses. And so there's the danger that these heavy masses, for example, the soft masses of these sigmas, will feed into your other masses at loop level. Okay.
Are you also imposing the experimental bound on W primes and Z primes?
Well, these guys do not. They have very, very suppressed mixing because their mixing is suppressed by F squared over U squared. So they have tiny, tiny couplings. So that there's no. It's going to be very, very hard in these kinds of models to see these gauge bosons. Maybe impossible. We haven't really checked, but.
Colored sigmas are.
Yeah, the colored sigmas are ripe for the picking. They're extremely model dependent, and I don't have anything to say about them. Take your favorite model of your favorite paper on SUSY with extra 5 + 5 bars. See that paper. That paper has the phenomenology. I mean, you have to ask, do they decay? If they don't decay, you've got R hadrons. If they decay, you have various signatures, right? So, yes, that's. But it sort of doesn't feed back into the Higgs phenomenology, so I don't really. It factorizes, so I don't say anything about it.
Because those colored triplets, they will never feed into the Higgs potential because of the extra quantum numbers you're saying.
Yeah, you can't write down any. I suppose you could write down a phi T bar type of. If T is your triplet, you could write down. And so that might somehow impact the phi potential, but it can't directly couple to the Higgs.
Can they couple to the top?
I guess, you could write H sigma triplet, just like you have just like a down type Higgs coupling. So you could write a coupling like this, right?
Yeah.
Or sorry, wait, what am I doing? No, phi. I mean something like, can you write this? No. I think hypercharge doesn't work. I don't know. We haven't looked at it.
Is there some quantum number that distinguishes them from the usual colored Higgs that are bad for proton decay? So
yeah, they're charged under a new gauge group, SU2S. Yeah, but you're worried about proton decay. You have to write down some operator. So if you want to write down some operator suppressed by M gut, you have to make it invariant under GS. To be honest, I haven't thought about it. We should just do the operator analysis. But my sense is that.
So I'm worried that M gut has nothing to do with it. They're colored Higgses at 2 TeV.
No, but they're not colored Higgses. They're triplets.
They can't couple. You can't write down Yukawa couplings of those triplets.
You can if you add enough powers of phi.
Okay, then you have a higher dimension operator. So it's higher.
By 2 TeV.
Okay. Well, let's talk about it. We can look at it. Let me just think. Do I have any simple answer to that? You're saying it's one dimension higher. It's dimension 5. It's a dimension, I guess it would be. So the basic point is that one way you can say it is that I can make phi times a triplet, where I contract the GS index, right? And this has just exactly the quantum numbers of an ordinary triplet, but it's one dimension higher, right? So I can write down some dimension 5 operator with a triplet. And so yeah, I guess if I believe that this operator doesn't respect baryon number, then I guess I have a problem. So I guess I would have to have some suppression of the baryon number violating part of that operator. I think you're right. But I think I'm willing to do that. Assume that. Okay. Okay. So there is the loop level tuning, but I just want to point out there's the leading loop level contribution. There's a loop contribution to the sigma mass that comes from the phi mass because they're both charged under the strong gauge group. But because it's just a gauge thing, it actually happens at 2 loops, right? So the nice thing about gauge interactions is that they feed scalar masses into scalar masses only at 2 loops, okay? So that really suppresses the tuning quite a bit. So even though I have this scale, which is in the multi-TeV range here, we include all these loop effects in the tuning, and this is the reason why they don't turn out to be very big, okay? And so if I plot this parameter space for this model, okay? I haven't told you exactly what the model is, but I'm trying to go from the bottom up. I'm trying to tell you about the mechanism and the important points rather than boring you with the model. I'll bore you with that at the end, I promise. Okay, so this is something like 3, 1. These are the values of GS. This is like 140. This is 246. And this is 180. Where's one? What's about there? That's fine. So then we have, whoops, sorry. We have the region that's ruled out by vacuum stability. So we just scan, right, and we just project down onto this space with some complete SUSY model, which I will show you in a second. If you're really hungry to know, I promise I will show you the theory, but you will just be bored. And then this is the Higgs coupling constraints, okay? And you can ask, and so GS of 3 really is, I think, this is really where I think I would start being worried about calling this a perturbative theory, okay? But you can change your mind if you want. And then you can ask, where do you get 10% tuning in this model? And the answer is this. Okay, something that looks like this. Maybe it doesn't go all the way up here. Maybe it looks something more like this. This is 10% or better tuning, is in this thing right here. And it's better than that sort of down here and whatever. There'll be a full plot, okay? And so this I like very much, okay? So first of all, this is not to scale. This is really close. If you get really close to this decoupling limit, of course you're tuned, right? But you don't want to be near there anyway. That's obviously tuning, and it is. But the point is that you get 10% tuning in essentially the entire phenomenologically allowed parameter space, okay? I mean, I am really getting tired of hearing talks where they say that they scanned 10 million parameter points and found 10 that were natural, right? This is not like that. I mean, it really is just natural. They're just the one thing you do have to do is the tuning is driven by this U right here. So the bigger I take this U, if I take the U bigger than this, I get more tuning, right? And so I have taken U to be the smallest thing that's allowed by the T parameter constraint. Okay, so that's the one thing that I've pushed to the limit to make this plot. Yeah.
Could you specify precisely what you mean by tuning 10% tuning?
Yeah, what I mean is what I mean is the usual thing that people compute, which is the sensitivity parameter log, d log, physical parameter, d log input, right? And I've taken the largest value of that. And the thing that it's dominated by is the fact is exactly this effect right here. It's dominated by this because I need the vev of f. I need this f to be small, right? On the other hand, this m phi needs to be big in order to satisfy this t parameter constraint. So that's totally what's driving the tuning. It's just that one effect.
That's computer with a 3-level potential?
I believe so. I believe that, well, No, I mean, this is a loop effect. So I think that this is not something where we plugged it into some gigantic big box. I mean, we just included the thing is that we included all the mass scales that need to be at the TeV scale, okay? And then we put in these effects. Oh yeah, and there's an assumption here. There's a log of a SUSY breaking scale, and that was taken to be 50 TeV. So we did take a low value for that. That's right. Yes. Okay. Yeah. There's a log here as well. Right. There's a log of some lambda here. Okay. That's right. Okay. So this is basically the final. This is the final result in terms of the phenomenology. Okay. And so now I'm actually going to bore you. The next thing I was going to do, unless you stop me by asking me questions, is bore you by telling you what the model actually is.
What about Higgs decay widths?
Higgs decay widths.
W's.
Oh, so you're saying that what about seeing these extra Higgses, right? Is that your question?
How are the Higgs branching fractions modified?
Well, that's what this constraint right here is. So this constraint right here is putting in the current constraints from LHC data that tell me what that have all the Higgs couplings, all the Higgs coupling constraints are giving me this excluded region right here.
Okay.
So that's put in.
Roughly, like, what is it? Are you saying it's like Higgs to WW goes down by factor?
Well, this is the experimental limit right here. So I'm trying to remember what drives this. I think it's actually. It may actually be the top coupling that drives this. I don't remember the reason. I mean, I don't remember which coupling sets this. I think it might even be the top coupling, but I'm not sure.
Fusion, the production.
Yeah, I mean, it's all the branching ratios. This is a global fit. Look, I mean, this is Jameson this is a real job of fitting the data, right? So they have an actual program that fits everything, and that's what gave rise to this.
Okay.
So I believe it's correct, even if I.
A deviation of the Higgs to the top, which reduces the global fusion, and then deviation of Higgs going to WW, no? So it is like
roughly speaking, right on this line, everything is perfectly standard model-like. And then it starts to deviate, everything starts to deviate as you go away from here. So you know that if you're sufficiently close to this line, it will just reproduce the standard model. And so we have some plots like this in our paper. You can see plots where you look at contours of constant, this coupling, that coupling, and they all just look like a bunch of lines parallel to this line. Okay? So we'll have some plots like that in the paper.
It looks like there's one mixing angle and you're just pressing all the couplings uniformly by power of the cosine of the mixing angle. Is that?
Well, that was true in that simplified two-parameter space. Here we're just scanning over everything, fixing these parameters and holding other
So you don't have that scrapulous going on in the full model as well.
I don't, but I bet Jameson does. Okay, I think, for every single thing we looked at, the simplified model gave you a pretty much perfect description of the phenomenology.
Of course, if that's what's happening, then branching ratios don't change. It's just the production rates.
Yeah, we checked everything with scans of the full parameter space, but yeah, I'm to be honest, I don't know exactly. I don't remember exactly what's breaking down first, and I don't know. I'm sorry.
Do you know how far we're expecting that limit to move in with, say, before the high luminosity upgrade kind of data?
I don't know. There are studies underway on this kind of thing. Scott maybe could comment. Roughly speaking, I would. Do you know by what factor the errors on the Higgs coupling? Let's say the Higgs coupling to gauge bosons. If it's the standard model, by the end of 300 inverse femtobarns LHC 14, do you know the factor by which the error will be? You don't know. People are working on that question, of course. I don't know the answer. But I think, to me, this is the big thing: is that I think it's kind of crazy to think that the 125 GeV Higgs state has nothing to do with the Higgs, right? Because it's got so many couplings that look standard model-like. On the other hand, the interesting game, I think, is does it mix with something else, right? Is there something else that it has and maybe has a reason to mix with? And then if it does, we have at least two different handles, right? One is Higgs coupling measurements, because we should expect a deviation there. And the other one is just direct Higgs searches, because those other excited auxiliary or whatever Higgses ought to couple to W's and Z's and tops and everything else at some level. And so we should just keep looking for heavier Higgses. And both of those things will constrain this parameter space. It's an interesting question. If we don't see anything at LHC with 300, LHC 14 with 300 inverse femtobarns, what's left? My guess is not much, but we should look at the studies, right?
So in your model, could the 125 be a heavy one?
I didn't look at that. We didn't look at that possibility. You can write that paper if you want. There's a region down here where that's the case. My guess is that you're going to have to tune something to get the couplings to work. So, but that's just, we didn't look at it.
I also have a question. I mean,
Yeah.
you're talking about the coupling limits on the Higgs that you have with 125.
Yeah.
Now there are exclusion, mass ranges of exclusion to very high masses, also for the standard model.
Yeah.
And so how does it affect the model in the case of the sigmas?
Well, we didn't do a careful job of this, but I looked at, for example, CMS Higgs to WW searches. I would guess that's one of the more sensitive ones. So you just look for a heavy Higgs going to WW. But the thing is that there is there's a coupling suppression here, and it looked so you can roughly fairly, at least the paper I looked at, for a fairly wide range of masses for the heavy Higgs, there you needed a coupling suppression, which I don't remember the number, but it was a fairly moderate suppression to get you underneath the bound, which looked very plausible to get here. So we certainly have not done a real phenomenological study, and we would like to do that, but it didn't look like it was just going to be immediately killed. Okay. So I think that is the crucial question here, is just what impact are direct Higgs searches going to have on this and the Higgs coupling measurements, and which one is going to rule out or discover this model first, right? So I think that's yeah. And I think it's also interesting, like I said, and here I can really say it, because now this is really a complete SUSY model. You can, and there's some half of this space right here. In this half of the space, the Higgs quartic is less than 1/2 of the standard model value. And by the way, a cute little fact is the tree level quartic in the MSSM is about half of the standard model value. So that's one measure of how much loop or something you need if you're trying to beef up the quartic. You need a factor of 2, roughly, in the quartic. So in about half of this region, you have a Higgs quartic, and therefore a cubic, which also deviates a lot. And one cute thing, if you don't know it, is that this actually means an increased rate for double Higgs production, because there's a destructive interference between the standard model and a QCD contribution. And so this actually means you get more double Higgs production, okay, not less. All right, so this is something that people are also trying very hard to convince themselves that they can do with 300 inverse femtobarns at the LHC. Okay. Okay, so shall I bore you with the model? I'm just about out of time, so I will bore anybody who wants to afterwards about the model. I'm just going to try to wrap up in a few minutes. Let me just say something. Some people care a lot about unification. So you can ask the question of, okay, in this parameter space here, where are the Lian-Tao poles? Because I need large values of GS, as you see here, right? So now the particular model that we're looking at, if I take SU2 strong S, this thing turns out to have 6 flavors. You can easily understand that because you have a 5 + 5 bar, plus you need that singlet phi. So this is the minimal model. And this thing has a 0-1 loop beta function. Okay, so that's already kind of cool. It tells you that this GS coupling runs rather slowly, even for large values of GS. But now there still are generically Lian-Tao poles. So there are 2 kinds of Lian-Tao. It's the minimal thing.
For what?
It's the smallest gauge group I can think of that's non-abelian.
So
it's nothing deep.
Technicolor anymore, so it's not necessary to have SU2.
I know, but I still take SU2 because it's the smallest minimal gauge group. Okay, you're welcome to take something else. Okay,
SP7.
it won't be as good and it will be less minimal. So there's nothing deep. There's nothing deep. Okay, so and then what you find, there's two kinds of Landau poles. If GS gets too big, GS has a Landau pole. But also if F gets too big, you get a Landau pole because you need the top quark mass to be what it is, and you need a bigger top quark Yukawa coupling the bigger you take F to be, right? Because sigma doesn't have any Yukawa coupling. So what you get for any given value, if you say, I don't want a Landau pole up to some scale, you will get something like this, okay? Some kind of limit that looks, say, like this, okay? And this particular one turns out to be 10 to the 3 TeV. Okay, so if you want to be 10 to the 3 TeV, you better be inside this little triangle right here. Okay? Now, of course, you want to know where's the gut scale, okay? And unfortunately, the gut scale is somewhere down here, okay? So this is lambda of 10 to the 16 GeV, okay? But now, the point is that what I can do, this is actually like 160 or something here to put in numbers, okay? Now you might say, okay, well, that's it. You're just as crappy as everybody else. But no, we're not. The reason we're not as crappy as everybody else is because all we need for this Landau pole, the Landau pole in GS, all we need to do is prevent GS from blowing up. Everything that's charged under GS comes in complete SU5 multiplets. So all we do is we assume that before some scale like this, we have some SU3 S prime that spontaneously breaks down to SU2 S. The detailed model is in our paper. This thing has 7 flavors. We need one more flavor because we need one more Higgs to do this breaking, to reduce the rank by 1. There's nothing deep about this model. This theory is asymptotically free. Okay? So that's it. We just match this thing onto, and it has complete SU5 multiplets. Any scale before this. In fact, if you really want to know more...
Produce more SU standard model, because there are fields that are charged under SU3 S prime cross SU5 standard model. SU5.
Yeah.
So you introduce more flavors at that scale.
I use one more flavor that's no more 5. There's one 5 plus 5 bar and 2 singlets under this SU3S. And one of those singlets gets a VEV at some high scale and breaks this thing down to SU2S. In fact, the more I talk about this model, the better it's going to be. You think it's going to be crappier the more I talk about it. It's the other way around. In fact, this model has, you are asking me, this model has a fixed point at strong coupling. It has this is in the conformal window. And so what actually naturally happens is that this goes to some strong fixed point, and then you break it. So the coupling is already strong there, and then it slowly decreases. So it's very easy to get these kinds of large couplings that you actually want in this model. Okay? So since you asked, okay. Now, okay, so there you do, so the bottom, but the take-home message is yes, if you really want unification, you need extra structure below the gut scale, definitely, but it's not that hard to make it. You don't need to do a snake dance or something to get it.
Marcus, other than the Higgs couplings changing and so on, how do you truthify it?
How do I what?
Truthify it.
Oh, well, I think you could go a long way. That's an interesting question. I mean, it would be a very interesting thing to ask, pick some point that's not super hidden at LHC. You see what you see. Certainly one hint, I do know any models in the literature that predict that the quartic is, less than half the standard model value. I don't know. Okay, it turns out it's hidden in the 2 Higgs doublet model, as I've said, so maybe you can find such things. But if you found this and you found these extra Higgses, you might be able to, you certainly have a lot of things that you can look at to try and I like that, truthify the model. Okay. So let me stop. I mean, we also looked at F-term models. So we looked at models where you have some superpotential term like phi sigma up, sigma down, where this is now just a singlet. So maybe I should call it S. So this is just like the NMSSM, except that these are the auxiliary Higgses. You can play that game. You get a parameter space that looks just like this. You don't have the T parameter issue. On the other hand, you have lower scale Landau poles. They're a little bit higher than in the NMSSM because there's no top contribution to this, which usually makes this guy run faster, but it still have low Landau poles, so that's it. And as far as phenomenology goes, the point is that these auxiliary Higgses cannot hide. They've got to show up. At LHC unless you're very close to this decoupling limit, I think. But of course, we're still faced with the problem that, as Guido Altarelli said already like 15 years ago, SUSY is late, right? And I have nothing to say about that problem. Okay, thank you.
Spencer and Rocky and John Killish probably have the new fat Higgs slimmer and more attractive.
Yes.
Which is not quite as much of a snake dance as.
Yeah. No, that's right. I just think, right. I don't have anything. I say let 100 flowers bloom. I don't hate other people's models. I think those are nice models. Yeah.
The longest data chooses yours, right?
I mean, like I said, I see my job as just saying, is naturalness really dead or not? And I'm desperately clinging to naturalness, right? Despite all of our smart colleagues telling us that we should give up on naturalness.
But how about the fact that what Altair says, we haven't seen any particles in already plain tuning?
I would suggest we discuss that over coffee. Yes, I mean I don't have anything new to say about that particularly.
So for the low-range spectrum, other than the usual MSSM, little h, capital H, and stuff, you have other Higgs fields?
Yeah, so there are these extra Higgses. In fact, I mean, a limit that is nice to think about, the Technicolor limit is actually simple because it decouples a lot of stuff. Okay, in the Technicolor limit, what you have is you have one set of goldstones from the Technicolor breaking, right? Then you have another set of goldstones from the Higgs bed, right? And so what happens is, in that case, the extra states that you have are turned into another pseudoscalar and another charged Higgs. So in that model, which is sort of the minimal version of this setup, you would have some stuff at the TeV scale, some Technicolor resonances and so on. And then instead of having a single A0, you'd have two A0s, which would be mixtures of the A0 that you have in the MSSM plus this extra thing, and you have two charged Higgses. Okay, but only two CP even Higgses. Okay, and in this theory right here.
How about the sigma of Technicolor? That could be an extra.
Yeah, but that's part of the TeV thing. So what I'm saying is that the spectrum below the TeV scale is model independent. And there's also a sort of pattern here, which is that the heavier one of these is dominantly the composite one, as you might expect. Okay, and so that one has reduced couplings to fermions, but it still has couplings to gauge bosons. So what I'm saying is that in this case here, there's a sort of definite pattern. It's not just extra Higgses. There's a definite pattern to their couplings, okay? And so you can say things like you expect some decay chain of Higgses to Higgses to dominate or not, or something like this. So actually at some point, Spencer Chang, Nate Craig, and I think that was pretty much it. And Jameson, I think. We were looking at the phenomenology of this, okay? There is a definite phenomenology of this, which I think is interesting, and but those people were all dragged off to more interesting projects. So the paper is not by people like Scott. So, yeah. Okay.
No one